Hi, everyone. This is our recording for the Platonic Academy of Melbourne geometry, the second part of geometry. So Platonic Esoteric Geometry, part 2, which we're running in the autumn sessions of our classes. And it was asked last night at our first session that I provide the slides, which is a bit tricky because the slides have a bit of animation on them. So I thought what I'd do is just go through the slides in this recording and just very quickly and roughly. And so that would just give something for people to refer back to, and probably the easiest way to review what we did on the slides, at least in the class today. So that's what I'm just going to do now. I'm going to bring up the slides and you can have a look at them and I'll just run through them. Okay, so hopefully now you're seeing slides. I will put it on. Okay, so here we go. So this is for the first week of Platonic Esoteric Geometry, part 2. And one of the things we started with is one of the things that we emphasized in the first class, just to get people warmed up, how to bisect an angle. So a very basic thing that we'll be doing all the time. So remember, what you do is you basically find a point on each of the lines equidistant from the vertex. Okay, and then draw circles the same diameter, same radius at those points. So find the cross of the two circles centered on a point equidistant from the vertex, and that will guide you to the bisection of the angle. So you can do that with acute angles, you can even do it with obtuse angles, and you can also do it with a straight line. So you mark a point on that line where you want to get your vertical axis, your right angle, and you do your two circles equidistant from that point, and that's how you get your right angle, or in this case, your north candle flame or vertical axis. Okay, so that's that basic technique which we use all the time, and it's one of the main things we do. Okay, now what I started with this week was just to say that firstly that why geometry is important in Platonism, and it's important as a gateway to understanding the formal nature of our experience. So if you understand how our experience of geometric forms relates to their formal essence, then this is a gateway, or a beginning, a way to come to an understanding of the formal essence of all our experience. Now, in this geometry, in Platonic geometry, it's all about symmetry and proportion. It's about relating same and difference, likeness and unlikeness through ratio or logos. So remember, there's two meanings of logos. One is like an account, a linguistic account. The other meaning is ratio, which you get in all Platonic geometry. A ratio is a this is to that, right? A relation of two things. In this case, it might be two lengths or two areas or something like that. This is to that, and you might say this is to that, as in this is double that, or this is half that. And we talk about a proportion where we say, well, maybe this is to that as that is to that. So A is to B as C is to D. So we might say that 1 is to 2 has a relationship of double. So 2 is double 1. You might say that 6 to 12 is also in the double ratio. In the Greek, ratio is logos and proportion is analogia. So if two things are in, if there's two ratios in the double, we say they are in proportion. And so we can think of this as like scale models, or in representational art. Everything is in the right ratio or proportion. We're very good at noticing proportion, and that is how we identify the same object near and far, right? A ship on the horizon compared to a ship up close. A scale model of a ship is like a ship far away. Consider a ship full size and the scale model, just as in the full size, one mast is to the other mast, so also in the model. The different parts have to be in the same proportion. And this is what we mean by the scale model being in scale, according to the scale, and so in proportion. And so also in representational art. So, for example, in the statue of David, we notice the beautiful proportions. And we notice also, if in art, for example, where the proportions maybe aren't quite right. And you see this a lot in poor art. But you might even look at the statue of David and you say, oh, are those hands too big? So we're really good at noticing proportion in our experience. So A is to B as C is to D is the internal proportions are right. But when we talk about the relation between, say, the two ships, or between the statue and the average person or the ideal person, we're talking about the scale. Like when you draw a plan for a house, it might be 10 mil is to 1 meter, or a map, 1 is to 100,000. So this is the logos ratio and analogia proportion, and its ratio, proportion, symmetry, or sameness, not difference, that Platonic geometry is all about. So we have A is to B as C is to D, that's the internal proportions, and to relate the scale, we have A is to C as B is to D. So the ratio of one mast in the full-size vessel to the scale is the same ratio as the ratio of the other mast to the other masts in the full-size scale. A full-size ship, as it is, sorry, I'll say that again. The ratio of one mast in the full-size ship is to the same mast in the scale model as the other mast in the full-size ship is to the other mast in the scale model. So that might be 1 centimeter is to 1 meter, or whatever else. So there's two ways of looking at proportion and ratio. Okay, so then we moved on to talking about geometry and doing the geometry on the page. So we talked about working in 3 dimensionals with the sphere, and then we talked about moving to the page. And making the first point on the page is to make the first distinction of the page. This is the distinction of the location or locus. So there is the sameness of the point. That is not its other. You find a place, you make a place, and that distinguishes the page as that place and not everywhere else. The point, in principle, has no length or width. It is, in principle, only a location with no dimensions. So we use a cross or a dot, some way to be able to see it. But of course, in principle, in the form, it has no dimensions. It's best to think of the point as piercing the page, making a gap or a hole. In this way, this first locus distinguishes indistinct space of the page with a particularity. The first particularity defines the page. And so this point is the primary reference of all else that proceeds in the diagram. This is our starting point. This is, in a way, kind of creates the particularity of the space. Now, the next most elementary in our geometry is the radius of the compass. So the radius of the compass defines a second point. It gives the scale of your diagram, right? The distance you move the compass in your very first drawing that you're going to make from that point, this sets the scale of your diagram, as we shall see as you proceed. In giving the scale of your it gives the scale of your diagram, so you mark a second point, and then we can think about all the other points equidistant from the previous point, the first point, and that gives you your first circle. Okay, next elementary to most of our geometry that we'll consider in this course is to take a point on the circle and make another circle. So we've already marked that in here. This circle runs through the center of the first circle and has a beautiful, simple symmetry. One way to imagine this is to consider it describing the second point like a satellite revolving around the first. So you have the first point and you have the second point as a satellite revolving around it, or the other way around. The second point is the center and the first point revolves around it. Or it can both be happening at the same time. Now, there's other ways to think about the symmetry in this diagram. That's just one. But in the European tradition, this is a very important basic geometric device. And it's often called the Vesica Pisces or the mandorla, meaning almond. So the Vesica Pisces means fish liver. I haven't seen a fish liver, but I have seen an almond. And so it is almond shaped. And in the European tradition, including Christian and Celtic, it's associated with the feminine power and especially the feminine power of reproduction. And by some curious coincidence, it's also similar to what we see in microscopic images of cellular division. Anyway, much of what we will be drawing in the coming weeks will start with the point, the first circle, and then the second circle drawn from a point on the perimeter of the first, the circumference of the circle from the first point. Okay, so then we moved on to looking at the square. Now remember, we drew a circle, and then we drew a square inside the circle, and then we drew a square outside the circle. And then by counting triangles, remember that we we were able to see how the square outside the circle was double the square inscribed inside the circle. Now, it helps to compare these two squares to the squares we drew in the first part of Platonic esoteric geometry. This was to solve the doubling of the square problem encountered in the first course by reference to Plato's Meno. Remember that. Remember that the problem of doubling the square was solved by drawing the square on the diagonal. And then we can see by mere inspection how the second square is double the first. We count the triangles, 2 triangles in the first square, and then we see 4 triangles in the second square. So the area must be double. And this gives us a particular case of the relationship expressed in Pythagoras' theorem. So with Pythagoras' theorem, the squares on the sides, the area of the squares on the sides, the 2 squares on the sides, equals the area of the square on the diagonal. And so we can add the area of those 2 squares just by counting triangles. So there's 2 triangles in each of the squares on the side, and there's 4 triangles in the square on the diagonal. And if we call the side of the first square 1, the monad square as it's called in Platonism, then the area of the first square is 1, because 1 times 1 equals 1. And the area of the second square we know must be 2 because it's double. But what, and it's also the 2 squares on the diagonal areas added together. But now, what is the length of the side of the second square? We know what the area is, but what is the length of the side? Well, it would be the square root of 2, because the sides of a square with area 2 would be the square root of 2, just like the sides of the square of area 1 will be the square root of 1, which is 1. And this square root of 2, as we know, can't actually be expressed as a ratio, and so it's called, its numeric expression is irrational. Now, perhaps we can do this again, of course. We can go to the second square and we can draw a square on its diagonal, and that square should be double the second square. What is the length of that diagonal in the second square? Well, if you have a look at the first square, we can see that it must be double 1. So the diagonal is 2, and so now we can build that next square with an area of 4. And so we've got a doubling series in the areas. And this can keep going on and on and on, and we did this in the first week. Okay, so in the areas, we've got an analogia, a geometric progression, as we call it these days, which is in the power of 2. So we're doubling. We're going from 1 to double 1 is 2, double 2 is 4. That's the areas. So we get this geometric progression progressing by the same logos. But what's happening with the sides? Right, the first side is 1, the second side is root 2, see there, and then the third side is 2, and the fourth side is 2 root 2. See how we can find all that from the first square, and we can keep developing and finding all the lengths and the areas just by the measurements of the first square. There's a diagonal of 4, and so on. So with the sides or the roots, the diagonal sides with that interplay, we're going, instead of 1 in the 2, 4, we have this intermediate term, the root 2 and 2 root 2 and so on. So what we're doing is multiplying by root 2. So with the areas, we're multiplying by 2 each time. With the roots, we're multiplying by the square root of 2. So how does this relate to what we just drew? Well, we can see how this diagram here, which relates to the diagram that Plato describes in the Meno, is a condensation of the first 3 stages of this expansion. So first of all, we've got that original 1 square with its diagonal, and then we've got the 2 square, the area of 2, and then notice how the diagonal of that square is also the side of the next square. And so the outside square has the area of 4. And so this is the same as our drawing where we drew a, and I'm sorry, I'm not showing that here, where we drew a square inscribed inside the circle and a square on the outside of the circle, touching its circumference. Okay, and I'll show this on this slide here. We've got the square on the outside here, and we're kind of doing this the other way. And you can go through this slide slowly yourself and notice the relationship between the circles and the squares, and how the difference, because the circles also double in their area as you go out. And they double on the ratio with the squares using the pi. So the relationship between the squares and the circles can be determined by the relationship between the ratio of pi. So if we have a look here in this stage of the diagram here, we can see for the outer circle, the diameter of 2 of the circle relates to the diagonal of the square. Okay, and we'll remember with pi is the ratio of the diameter of the circle to its circumference. So if its diameter was 1, then its circumference would be pi, which is like 3.14 or whatever. And if it's 2, obviously it would be pi times 2. So we can see how the circles and squares relate to each other in these ratios of root 2 and pi. Okay. So the final slide we had for the first week is to show how these circles and squares are often used in sacred architecture, East and West, and also they're used in mandalas, meditation mandalas in the East. So here I just pulled out a diagram which is quite interesting from the Renaissance design of a cathedral, where the cathedral is also considered to be on a biometric model. So we have the shape of the cathedral related to the shape of the human body. And so this is a way of seeing how in Renaissance humanism, that the human is related to the divine through geometry, and in this case, the geometry of squares inscribed in circles. Okay, so that is the slides for the first week. I hope that was helpful in revising what we were doing and in moving on to the next part of the course. Now, a couple of things that I did also show, which might be helpful, is that, and if we can see this here, how you can continue the squares and circles inscribed. You can continue down into smaller squares and circles, and you can continue out by the same process that we used to create the first two squares and circles. And you can also do your squares where they're not static and dynamic, so where they are sitting flat, if you like, and you'll still get the same proportions. You'll still get the doubling squares, and you'll often see that in geometry too. And the last thing was to show that you can do logarithmic spirals using those circles here, where you step out to a new circle on the spiral, maybe a quarter of a turn, you curve your circle out towards the next circle. It's not very clear on there. So if you want to find out more about how to make that spiral, I can explain it to you. So it looks a bit like a shell. So all those natural spirals that we see, where the distance, the inner distance between one line and the next line is less than as you go out. So the distance between the lines gets greater as you go out. They're called logarithmic spirals, and some of them are golden ratios. Some of them are on different ratios as well. Often people will say that they are golden ratios, but they can be on, they're often found to be other ratios. The main thing is that they're logarithmic spirals, and you can make a logarithmic spiral out of the square root of 2 ratio, as well as the golden ratio and the ratio of double or whatever. All right. So that's probably enough. Okay. Thanks for listening, folks. And I'll see you next week.